For a very long time, humans have imagined what life may be like in other worlds. Thanks to the James Webb Space Telescope, the most powerful telescope in existence, that question can finally be answered. While observing the closest star system to us, Proxima Centauri, which is only 4 light-years away, scientists have noticed some peculiar anomalies from one of the planets in the system, Proxima B. These anomalies, called artificial lights, have puzzled the best minds in the scientific community. But what are they? Do these lights suggest the existence of intelligent life on the planet? Join us as we explore James Webb's terrifying discovery of city lights that changes everything. The only life that we are currently aware of is on Earth. Since the beginning of civilization, people have questioned whether there is life elsewhere in the universe. To carry out such an interstellar search, American astronomers Jill Tarter and Thomas Pearson launched the search for extraterrestrial intelligence, SETI project in 1984. The project's objective is to gather spaceborne radio signals. Radio waves can travel farther and are therefore more likely to be detected by the 42 radio telescopes that make up the unique Allen Telescope Array in the Californian Cascade Mountains. This is because radio waves are less dispersed or absorbed than other types of radiation. However, in the past 30 years, no verifiable alien signal has been discovered. Following the James Webb Space Telescope's successful launch, the quest for extraterrestrial life has gained momentum. The telescope was designed to examine a range of distant, undiscovered planets orbiting far-off stars. As the largest telescope in the world, floating roughly 1 million miles from Earth and outfitted with incredibly sensitive detectors, the James Webb Space Telescope is capable of observing distant celestial bodies with unprecedented detail. 20 years ago, there were no known planets outside our solar system, but since then, more than 4,000 exoplanets have been discovered orbiting other stars. According to NASA, the universe may contain trillions of exoplanets. The earliest signs of life beyond our solar system may be found in extraterrestrial plant life. The Galileo spacecraft, on its route to Jupiter, turned its equipment back toward Earth and found a definite indication of the presence of plants. The instrument detected the vegetation red edge, VRE, biosignature, a mix of red and infrared lights reflected by plants. For instance, a planet like Earth that is covered in jungle should have a strong and easy-to-detect VRE signal. The James Webb Space Telescope will measure the VRE of far-off Earth-like planets in the habitable zone around stars. These could be important signs of life in the exoplanet's atmosphere. When sunlight crosses a planet's star, the James Webb Space Telescope may be able to detect it as it enters the planet's atmosphere. The missing wavelengths of light would then be discovered via spectroscopy. Atoms and molecules in the atmosphere absorb specific wavelengths, creating a characteristic fingerprint that the telescope can recognize. This method may be used to determine the composition of the atmosphere and whether life is possible. It is likely that life could exist on Earth-sized planets with atmospheres similar to our own, with a predominance of oxygen, nitrogen, and carbon dioxide. By looking for elements that aren't usually present, one may be able to detect technological life. Chlorofluorocarbons, CFCs, generated for use in refrigeration and cleaning products, would probably be noticeable to aliens monitoring Earth's atmosphere from a distance. If the James Webb Space Telescope found CFCs in planetary atmospheres, it would be a clear indication of civilization. However, life on exoplanets might not even remotely resemble life on Earth. Sometimes even earthly life forms, like extremophile species, can seem alien. Extremophiles are organisms, primarily bacteria, that can endure environments where other living things would perish. Some humans can withstand heat up to 250 degrees Fahrenheit, while others can endure colds as low as -4 degrees Fahrenheit. Some extremophiles can survive in strong acids with pH levels below 3, while others can be found in places where we would not expect to find any life at all. Since planets like Earth are more likely to support life than planets with severe temperatures or acidic conditions, it is a good idea to start with those first. Prime candidates could have temperatures that allow liquid water to exist on their surfaces and/or orbit a stable star. The classification for our Sun is a yellow G-type star. These stars are less common and typically have shorter lifespans in our universe. The likelihood of studying planets orbiting around red dwarf stars, which are more frequent and have lower luminosities and temperatures than the Sun, is higher. There is more time for the formation of life and evolution to produce complex life forms because these stars have significantly longer lifespans. Around 40 light-years away from Earth, the TRAPPIST-1 planetary system will be the subject of the James Webb Space Telescope's first mission. It revolves around a calm red dwarf star with 7 Earth-sized rocky planets. 3 of these rocky planets are in the so-called habitable zone and might have liquid water on their surfaces. Despite having a much smaller and colder mass than our Sun, the TRAPPIST-1 star radiates light that is similar to that of Earth. The best chance for humans to see city lights outside the solar system is Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun and our nearest star. Proxima Centauri is about 600 times fainter than the Sun, so a planet must be 20 times closer to it than Earth is to the Sun in order for it to support life based on liquid water. In August 2016, astronomers discovered a planet with 1.3 Earth masses in this habitable region, in a Goldilocks-like habitable zone where the light intensity is just right to melt water. Proxima B circles Proxima Centauri, and it is possible that Proxima B is an airless, lifeless planet given that it orbits its red dwarf star at a distance of only 4.6 million miles. The distance between the Sun and Earth is 93 million miles. Proxima B's close orbit exposes it to strong solar winds that can completely destroy its atmosphere. It also provides enough sunlight for temperatures and liquid water that are similar to those on Earth. Because of its close proximity to the star, Proxima B is thought to be tidally locked, always showing the same side to the star, similar to how the Moon does in reference to Earth. Proxima Centauri is about 1/8 the mass of the Sun and burns far less brightly than one might anticipate for a planet so near to its star. Just 5% of the Earth-Sun distance may be anticipated to be a red-hot cinder. Liquid water could easily exist on Proxima B as long as the planet has an atmosphere to hold heat in, since the total energy reaching it from the Sun is only 65% of what Earth receives. However, the planet is not especially friendly to life. It is most likely tidally locked, which means it always faces the same direction toward the star and produces permanent day and night sides with significant temperature changes. The planet also receives 100 times as much high-energy radiation as Earth does, including X-ray and ultraviolet light. Proxima B is also bombarded with high-energy particles during star flare-ups. Unless it has a shielding magnetic field similar to Earth's, its atmosphere could be at risk. Certain realistic conditions could make it a pleasant world, but models suggest that the atmosphere of tidally locked planets may be susceptible to a rapid collapse due to the freezing out of volatile gases on the night side. Earth's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, the atmosphere is less likely to escape. Since we don't know anything about Proxima B's volcanic activity or magnetic field strength, we can't even guess whether or not the planet has an atmosphere. But since an atmosphere presupposes the existence of seas and the two taken together presuppose the existence of life, we are desperate to know if Proxima B has a sophisticated civilization. It might have solar panels covering the day side to generate electricity to light and warm the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima B has triggered a race to determine if it crosses its star's face as seen from Earth. These transits would let scientists determine the planet's size and mass, which would then enable them to determine its density. Knowing that would validate the planet's rocky makeup and provide information on the materials used to create those rocks. During a transit, starlight might disclose the nature of the planet by passing through its atmosphere. However, the likelihood that the orbit will be in the right alignment for scientists to see a transit is merely 1 in 12%. The star's propensity to flare also complicates matters. Astronomer David Kipping of Columbia University says the star is tricky, as its heat causes a rocky planet to absorb sunlight and radiate it as infrared light. However, rocky planets produce a distinct type of infrared radiation from stars like Proxima Centauri. Additionally, the James Webb Space Telescope was created specifically to study infrared light. Proxima B's infrared heat signature is key to identifying the planet's atmosphere. The infrared portion of the spectrum has a strong affinity for Hubble's successor. Researchers will be able to measure the amount of water vapor in the atmosphere, constrain the abundance of different elements like carbon and oxygen, and estimate the temperature of the atmosphere with depth using the spectrum that Webb is planning to observe. They can use the data to draw conclusions about the planet's overall composition as well as how, when, and where it formed. The best fit model represented by the blue line on the graph accounts for the data, the known characteristics of WASP 96b and its star, as well as the ascribed properties of the atmosphere. Modern web design has made it possible for these measurements to have such exceptional clarity and detail. The 270-ton, gold-plated mirror effectively captures infrared light. Its sensitive infrared detectors detect incredibly minute variations in brightness, and its precise spectrographs disperse light into rainbows of thousands of infrared colors. An IR-cam can distinguish brightness differences between colors that are a few hundred parts per million apart and color differences that are only a few thousandths of a micron apart. It covers infrared light wavelengths that we have never had access to before, which is exciting. The infrared atmospheres of exoplanets have been studied by other telescopes, but not with the same level of detail. This is only a small portion of the data. According to Colin, an expert on exoplanets, in addition to Webb's extreme stability, its orbital location around L2 and its distance of about 1 million miles from Earth's atmosphere allow for an uninterrupted view and quick data analysis. Only a glimpse of what Webb will bring to exoplanet research is shown by the incredibly detailed spectrum created by analyzing 280 individual spectra simultaneously. Researchers will use spectrography to examine the atmospheres of dozens of exoplanets, ranging in size from small rocky planets to giants that are abundant in gas and ice over the coming years. Exoplanet research and the materials it produces take up almost a quarter of JWST's cycle. In one observation, this closest observation demonstrates Webb's capability to describe exoplanet atmospheres, including those planets that may be habitable. The majority of the science, according to Antonella Nota, a JWST scientist who oversees the European Space Agency's office at the Space Telescope Science Institute, will be conducted using spectra. While we often say that a picture is worth 1,000 words, astronomers only consider spectra to be worth 1,000 pictures. With that, today's episode comes to a close. We can only hope that the James Webb Space Telescope's enigmatic discoveries continue to surprise us with new information about exoplanets. The James Webb Space Telescope, JWST, represents a monumental leap forward in humanity's ability to study distant worlds and unravel the mysteries of our universe. Launched with the promise of pushing the boundaries of astronomy, JWST is poised to revolutionize our understanding of exoplanets, particularly in the realm of their atmospheres. One of the key innovations of JWST lies in its sheer size and capabilities. Sporting a massive 6.5-meter primary mirror coated with a layer of gold to optimize infrared reflection, JWST dwarfs its predecessor, the Hubble Space Telescope, in both size and sensitivity. This large mirror enables JWST to gather unprecedented amounts of light from distant celestial objects, allowing for detailed observations that were previously unattainable. Moreover, JWST is equipped with cutting-edge instruments tailored for high-resolution spectroscopy and imaging across a wide range of wavelengths, particularly in the infrared spectrum. This capability is crucial for studying exoplanets, as infrared light can penetrate through cosmic dust clouds that obscure visible light, providing clearer views of planetary atmospheres and surface features. One of the primary objectives of JWST is to conduct detailed spectroscopic analyses of exoplanet atmospheres, such as WASP 96b, to detect and characterize key chemical compounds. By observing how starlight passes through an exoplanet's atmosphere during transit, JWST can create transmission spectra that reveal absorption lines corresponding to different molecules such as water vapor, carbon dioxide, methane, and more. These absorption lines act as unique fingerprints that allow scientists to identify the composition of an exoplanet's atmosphere and make inferences about its physical conditions such as temperature, pressure, and weather patterns. For instance, the presence of water vapor in an exoplanet's atmosphere could indicate the potential for liquid water on its surface, a critical factor in assessing a planet's habitability. In addition to studying individual exoplanets like WASP 96b, JWST aims to conduct comparative studies of exoplanet atmospheres across different types and sizes. By analyzing a diverse sample of exoplanets, ranging from hot Jupiters to Earth-like planets, Scientists hope to uncover patterns and trends that could shed light on the formation and evolution of planetary atmospheres in general. Furthermore, JWST's capabilities extend beyond exoplanet research to encompass a wide range of astronomical investigations. The telescope's deep-field observations will probe the early universe, capturing the faint light from the first galaxies that formed after the Big Bang. These observations promise to reveal crucial insights into cosmic evolution, galaxy formation, and the origins of heavy elements essential for life. The development and construction of JWST have been a testament to international collaboration and technological innovation. Led by NASA in partnership with the European Space Agency, ESA, and the Canadian Space Agency, CSA, JWST represents a global effort to push the boundaries of space exploration and scientific discovery. Despite numerous technical challenges and delays, JWST's successful launch and deployment in 2021 marked a historic milestone in space exploration. The telescope's journey to its operational orbit at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth, was a testament to human ingenuity and perseverance in overcoming complex engineering obstacles. Now fully operational, JWST is poised to embark on a mission of unprecedented scientific exploration. Its ability to peer deeper into space and time than ever before promises to revolutionize our understanding of the cosmos and our place within it. From unraveling the mysteries of exoplanets to probing the origins of galaxies, JWST stands at the forefront of astronomical discovery in the 21st century. Looking ahead, JWST's legacy will extend far beyond its initial mission lifespan of 10 years. The data collected by JWST will serve as a treasure trove for astronomers and scientists for decades to come, fueling countless research projects and breakthroughs in astrophysics, planetary science, and beyond. Moreover, JWST's role in inspiring future generations of scientists and engineers cannot be overstated. The telescope's groundbreaking discoveries and captivating images of distant worlds will ignite curiosity and fuel dreams of exploration among young minds worldwide. In conclusion, the James Webb Space Telescope represents a pinnacle of human achievement in space exploration and scientific discovery. With its advanced capabilities and unprecedented sensitivity, JWST is poised to uncover the secrets of the universe and reshape our understanding of cosmic evolution. As JWST continues to peer deeper into the cosmos, it holds the promise of revealing new wonders and answering age-old questions about our place in the universe.